Now, the behavior of gases. Now see here, the behavior of gases based on behavior of gases are based on some assumptions. Okay, behavior of gases. Behavior of gases are based on some assumptions, okay. Now see here, let us consider a container. Okay, let's consider container. Suppose we are inserting the gas, okay, and we close this container. Okay, now see here, there are some small tiny particles. There are some small tiny particles. These small tiny particles are known as molecules. These small tiny particles are known as molecules. So first assumption is a matter consists of small tiny particles. Small tiny particles are known as molecules. Okay. The first assumption is that a matter or a gas consists of small tiny particles. That such small tiny particles are known as molecules. Okay. Now see here, these small tiny particles are mostly random motion. They are moving in random motion. Okay, that means they are not moving in a perfect direction or same direction. Okay, this molecule is moving in this direction, this molecule is moving in this direction. That means directions of each molecules are different, and these molecules are moving randomly. Okay, in container. Okay, so the molecules, second assumption, molecules are always in random state of motion. Random state of motion. Okay. Now see here. Suppose this molecule we name as A molecule. Here is the B molecule. Okay. Then the force of attraction between these two molecules are negligible. The force of attraction between two gaseous molecules are negligible. That means they exist. The force of attraction between molecules. Okay. So the third assumption, that is the intermolecular forces between two molecules are negligible. That means the force of attraction, the range of the force of attraction between two gaseous molecule is very short. That is approximately equal to 0. That means it is negligible. Okay. And suppose we insert this gas in this vessel. Suppose the shape of this vessel as like this. Okay, then this gas is same gas is inserted in different vessel. Okay, now see here the shape of gas molecules are not same. Okay, that means they occupy the shape and volume. Okay, they occupy shape and volume of that vessel in which they are inserted. बघा हा काय केला आपण कंटेनर घेतला बरोबर आहे याच्यामध्ये काय केला गॅस इन्सर्ट केला गॅस इन्सर्ट केल्यानंतर या गॅसने काय केलं हा कंटेनरचा काय केला शेप ऑक्युपाय केला व्हॉल्यूम ऑक्युपाय केला बरोबर आहे विथ दोज गॅस सेम गॅस इज inserted in different vessel then that gas occupies the shape of given vessel and also occupy the volume of a given vessel. Okay, that means the gases do not have definite shape and volume. Definite shape and volume. Gases do not have their own shape and not have their own shape and volume. Own shape and volume. Okay, these are the basic assumptions. These are the basic assumptions. Now see, I can again explain here. Matter consists of small tiny particles. A matter consists of small tiny particles are known as molecules. Okay, so you see here, this is the gas. Okay, this gas is inserted in this container. So the gas, the small tiny particles of the gas are known as molecules. Okay, now next one, the molecules are always in a random state of motion, or the gas molecules are always in a random motion. Now see here, this molecule is moving in this direction, this molecule is moving in this direction. Okay, so different molecules are moving in different direction. Okay, that means these molecules are in random motion. They are always in a random motion. Okay, next one, the intermolecular forces between two molecules are negligible. That means here suppose A is the first molecule and B is the second molecule of a gas. Okay, then there is a force of attraction or intermolecular forces as like adhesive force, cohesive force we had already learned. Okay, now the intermolecular forces between these two molecules are approximately equal to 0. Are approximately equal to 0. That means they are negligible. They are negligible. And next one, the gases do not have their own shape and volume. See here, the gas is inserted in this rectangular container, then that gas occupies rectangular shape and also occupy the volume of that given container. I change only that vessel or container of different shape. So I insert this same gas in this container, then that gas occupy as like this shape. That means the gas occupies That means that gas do not have their own shape and their volume. Now next one, the gas laws. Okay. Now the first law, that is Boyle's law. Okay. We have already learned in previous years. Okay. Now what is the statement of Boyle's law? Okay. For a given mass of a gas, for a given mass of an ideal gas at a constant temperature, volume of a gas is inversely proportional to its pressure. Okay, see here. For a given mass of an ideal gas at constant temperature, I can write here, at constant temperature, the volume of given gas, is inversely proportional to its pressure. Okay. Let T be the temperature, V be the volume of a gas, and P be the pressure of a gas. Okay. Now see here, the volume of a gas is inversely proportional to its pressure. That means therefore V is inversely proportional to its pressure. When volume of a gas is inversely proportional to its pressure, when at constant temperature. Calling it equation number 1. When the for a given mass of an ideal gas at a constant temperature, the volume of given gas is inversely proportional to its pressure. That means V is inversely proportional to P. Okay. So therefore PV is equal to constant. Okay. Now see, by using the formula for density is equal to mass upon volume. Therefore volume is equal to mass upon density. Therefore PV is equal to P into mass upon density. Okay. So mass upon density is equal to constant. Okay. This is the which law? Boyle's. Okay. Now second one, that is Charles law. Second one, that is Charles law. Okay. Now see here, for a given mass of an ideal gas at a constant pressure, the volume of a gas is directly proportional to its temperature. See here, for a given mass of gas is directly proportional to is directly proportional is directly proportional to at a constant pressure volume of a gas is directly proportional to its temperature. Therefore, it can be written in equation form, that is V is directly proportional to T. When volume of the gas is directly proportional to temperature, when at constant pressure. Equation number 2. When the pressure of given gas is constant, then the volume of gas is directly proportional to its temperature. So V upon T is equal to constant. V upon T is equal to constant. So therefore volume is equal to mass upon density. Therefore mass upon density into time is equal to constant. Okay, so this is the charge law. This is the charge. Now next one, that is Gay-Lussac's law. Third one, Gay-Lussac's law. Okay. At a constant volume, what is the statement of Gay-Lussac's law? At a constant volume of or for a given mass of an ideal gas, at a constant volume, the pressure of a gas is directly proportional to its temperature. Okay, that means for a given mass of an ideal gas at constant volume the pressure of gas is directly proportional to its temperature. Therefore, we can write the pressure is directly proportional to its temperature when at constant volume. Calling it equation number 3. Okay, at constant volume, therefore P upon T is equal to constant. P upon T is equal to constant. This is the Gay-Lussac's law. Okay, these 3 laws. Okay, now see here. Now see, there are 3 laws of gases. First one, that is Boyle's law. What is the statement of Boyle's law? For a given mass of an ideal gas at constant temperature, the volume of given gas is inversely proportional to its pressure. That means V is inversely proportional to P. When V is inversely proportional to P, at constant temperature. Therefore, PV is equal to constant. Okay. Now, by using the formula of density, density is equal to mass upon volume. So, volume is equal to mass upon density. Therefore, PV is equal to P into M upon rho, which is equal to constant. This is the Boyle's law. Now, next one, that is Charles' law. For a given mass of an ideal gas at a constant pressure, the volume of gas is directly proportional to its temperature. Okay, that means V is directly proportional to T. When V is directly proportional to T at constant pressure, V is directly proportional to T. Therefore, V upon T is equal to constant. Okay, so V upon T is equal to, similarly by using the formula for volume is equal to mass upon density. So V upon T is equal to M upon rho into T, which is equal to constant. Okay, now next one, that is third law, Gay-Lussac's law. Okay, for a given mass of an ideal gas at a constant volume, the pressure of a gas is directly proportional to its temperature. That means P is directly proportional to T. Therefore, P upon T is equal to constant. Okay, these are the three laws. Okay, now see here. For from Boyle's law, at a constant temperature, volume of a gas is inversely proportional to pressure. By Charles' law, at a constant pressure, volume of a gas is directly proportional to temperature. Gay-Lussac's law, at constant volume, P is, that means pressure is directly proportional to T. So, combining equation 1, 2 and 3. So, we get combining equation 1, 2 and 3. Combining equation 1, 2 and 3, that is PV is directly proportional to T. Okay, from equation 1, 2 and 3. Okay, so PV is directly proportional to T. Therefore PV upon T is equal to constant. PV upon T is equal to constant. Okay. Similarly, we can write for P1 upon T1 is equal to P2 V2 upon P2 is equal to constant. Okay. So, calling this equation number 4. Okay. Now see here, let n be the number of moles, n be the number of moles, n be the number of moles. So PV is directly PV is directly proportional to NT. PV is directly proportional to N into T. Okay. So where N is the number of moles, that means mass of gas divided by molar mass, that is equal to M upon M0, that is M upon M0, which is equal to N upon Na, which is equal to N upon Na. Okay. Now see here, we are using this equation. Okay, so we get PV is directly proportional to T. Boltzmann constant is equal to PV upon N into T. Okay, Kb is equal to PV upon N into T. Therefore, Kb is equal to P1 V1 upon N1 T1 is equal to P2 V2 upon N2 T. Okay, this is equation number 5. Okay, this is called as a Boltzmann constant. Okay, now we have already knowing the perfect gas equation or ideal gas equation, that is PV is equal to nRT, where R is the universal gas constant and it is equal to Na into Kb. Okay, Na into Kb, where Na is the Avogadro's number and Kb is the Boltzmann constant, and R is also known as universal gas constant. Universal gas constant. So the value of R is, the value of universal gas constant is 8.314 joule per mole Kb. Joule per mole Kb. And the value of Boltzmann constant is, 1.38 into 10 raised to 1.38 into 10 raised to minus 23 joule per Kg. Joule per Kg. Okay. Now see here, we are using the three gas laws. That means first law is Boyle's law. In Boyle's law, at a constant temperature, the volume of gas is inversely proportional to its pressure. According to Charles' law, at a constant pressure, volume is directly proportional to temperature. And Gay-Lussac's law, at constant volume, pressure is directly proportional to temperature. Okay. Now combining these three equations, we get PV is directly proportional to T. Okay. That means PV upon T is equal to constant. For gas 1, we can write P1 V1 upon T1. For gas 2 is equal to P2 V2 upon T2, which is equal to constant. Now N is the number of moles. Okay, N is the number of moles. Therefore PV is directly proportional to Nt, where N is equal to mass of a gas upon molar mass. So M upon M0, which is equal to N upon Na. Okay. Now we are using again that equation, PV is directly proportional to T. So proportionality sign can be neglected by using proportionality constant. So PV is equal to Kt. So K is equal to N into Kb, where Kb is the Boltzmann constant. So substituting the value of K in above equations, so we get PV is equal to N Kb into T. Therefore Boltzmann constant Kb is equal to PV upon Nt. Okay. So we know that the perfect gas equation or ideal gas equation, PV is equal to nRT. So R is the universal gas constant. So therefore R is equal to Na into Kb, where Na is the Avogadro's number. The value of universal gas constant is 8.314 joule per mole Kelvin, and the value of Boltzmann constant is 1.38 into 10 raised to minus 23 joule per Kelvin. Now see next point, that is assumptions of kinetic area of gases. Okay, some assumptions which is related to the nature of gas, which is related to the nature of gas. Now see here, first, a gas consists of large number of tiny particles called as molecules. A gas consists of large number of tiny particles, that is very small particles, are known as molecules. Okay. Now next one, the molecules are rigid and perfectly elastic spheres. Molecules are rigid and perfectly elastic spheres. Perfectly elastic sphere. Now next one, all molecules of the same gas are identical in size, shape and mass. All gas molecules of the same gas, see here, all gas molecules of the same gas are identical in size, shape and mass. Condition is applied here. The molecules which are of the same gas. Suppose A is the molecule of CO2 and B is the molecule of nitrogen. Then these two molecules are different in size, shape and mass. Why? Because the gas is different. Okay. Now see here, all the molecules of the same gas are identical in size, shape and mass. Okay. And last one, that is the actual volume occupied by the gas molecule, is very small as compared to the total volume occupied by the gas. Suppose this is the container, and in this container, suppose CO2 gas is there. Okay, this container is closed. This CO2 occupies the shape and volume of given container. Okay, now there are small tiny particles. Such particles are known as molecules. The volume occupied by a molecule is very small as compared to the volume occupied by the gas. Okay, so the last one, assumption, that is actual volume occupied by a gas molecule is very small as compared to the volume occupied by the gas. Okay, these are the assumptions related to the nature of gas. Now next assumptions, which is related to the random motion of a gas molecules. Now see, the molecules are always in a state of random motion. The molecules are always in a state of random motion, that is, they are moving in all possible directions with all possible velocity. Suppose this is the container. In this container, the gas is closed or enclosed. Okay. Now there is a small tiny particles. The tiny particles are known as molecules. These molecules are moving in all possible directions. With all possible velocities. Okay. So this is the assumptions related to the random motion of gas. Next one, due to random motion the molecules constantly collide with each other. The molecules are constantly collide with each other, and also the walls of container. Now see here, these molecules are constantly collide with each other and also on the walls of container. Okay, also the walls of container, since the collision is perfectly elastic. The collision is perfectly elastic. That means there is no loss of kinetic energy during collision. Then that collision is known as perfectly elastic. What is the perfectly elastic? There is no loss of kinetic energy. There is no loss of kinetic energy during collision. Such collisions are known as perfectly elastic collision. Okay. And next one, between two successive collisions of a molecule travel in a straight line. Between two successive collisions of a molecule travel in a straight line with a constant velocity. With a constant velocity, it is known as free path. It is known as free path. Okay, these are the assumptions related to the random motion of a gas molecules. Okay.